And I have the privilege of opening the morning session with introducing Jonathan Fortney, who will tell us everything we need to know about exoplanet atmospheres, or at least get us observers set straight.
All right. Can everybody hear me okay? Yes. All right. Okay, well, it's great to be here. I was looking over at the conference photo from 2007, and I saw myself in the second row. I was a postdoc at the time, and now I've been a professor for 18 long years since then, and it's really been great to see so much about direct imaging and exoplanet atmospheres change over time. There's lots of really interesting, familiar faces I'm seeing. I'm sorry I wasn't able to be here earlier in the week. Had some teaching obligations, but I found somebody else to give the midterm exam for Friday, so I'm here now. I'd like to thank the organizers. They sort of asked me to give an overview, but also sort of a state of where things are for atmosphere models and where they're going and the different varieties. So I am going to do that, but I also thought it would be interesting to sort of talk about a particular science topic that I think we've made a lot of progress on in the past few years. That's sort of at the interface of imaged giant planets and brown dwarfs. So I'm going to spend some time talking about that as well, sort of in the middle of the talk. Then towards the end, I'll talk a little bit about where I think we're going and how how modelers are trying to react to new science that's happening on the observational side. So people often show slides like this, the things that we're trying to do in terms of atmosphere models. We're trying to look at the spectra. This is a cool pointer. I've never used one of these before. Cool. We can just sort of wave it around. We want to understand how planets work. We want to think about the temperature structure, how that might change with time. We want to think about the atmospheric abundances that we see and what that tells us about the physics and chemistry of atmospheres, this general idea of how planets work. That's, of course, been a long topic in the solar system, and now we have such a wide variety of planets in different distances from the star, different masses. We can really build a comprehensive idea of that in a much larger phase space. We're also all astronomers. Astronomers really love to understand origins. Where do planets come from? And so we also want to be able to look at atmospheric abundances to perhaps learn something about planet formation process, be it if it's a giant planet, the metallicity of the atmosphere, the carbon to oxygen ratio. These are things we want to be able to interpret from spectra that we have. And so just to sort of follow up on these same two themes, often one of the things we can see in the atmosphere are abundances of maybe carbon and oxygen-bearing molecules, water vapor, CO, CO2, other things like that, maybe photochemical products. And again, atmospheric physics and chemistry and sort of planet formation both dictate these sorts of abundances. On the right, we can see this is a paper from over a decade ago now, looking at the methane to CO ratio. Black is CO-rich, white is methane-rich over a very large phase space. And you can see, hot planets CO-dominated, cool planets methane-dominated. That also affects the water vapor abundance via that chemical reaction between those two. And as we get to cooler and cooler temperatures, those abundances change, but we also have to worry about whether or not we're dredging up gas from deeper in the atmosphere, which I'll spend a lot of time talking about today, and how that also can change the abundances we might see in the visible atmosphere if we're dredging up gas from deeper down. Also, there's a famous plot on the left-hand side sort of reminding us that when we're accumulating a giant planet, that's a mixture of gas that has its own carbon-to-oxygen ratio, solids, which has its other carbon-to-oxygen ratio. The final planet's a mixture of those solids and gases that are all sort of vaporized in the atmosphere. That also is going to dictate the atmospheric abundances that we see. So we always should be mindful of that. So talking about atmosphere models, someone once told me it was sort of like baking a cake. There's lots of ingredients you have to put in, and then your final thing is either the cake or the model atmosphere at the end. So there's lots of different choices you have to make. These are just the ones that I was sort of thinking about this over time. And so you have to think about if your planet's near a star or not. If you have some sort of input spectrum from the star that might heat the upper atmosphere. You also have flux coming out of the planetary interior. Classically, for directly imaged giant planets, that's the dominant energy source. We're looking at young planets. Surface gravity can have a major effect in the atmosphere. Your base elemental composition, the metallicity of the atmosphere you're trying to model, or the carbon to oxygen ratio, you might want to try different ones of those out. If you're thinking more about terrestrial planets, your base atmosphere, be it O2 dominated, nitrogen dominated, CO2 dominated. You have to have some treatment of chemistry, be it equilibrium chemistry or non-equilibrium chemistry. We're thinking about timescales of mixing. You have to have some sort of treatment of clouds. This is one bullet point, but you can imagine tons of sub-bullet points about how you're treating clouds. Clouds, as we know, have a big impact on atmospheric spectra. Also, mixing processes down below is, do you have adiabatic convection, or are you super adiabatic or sub-adiabatic? You also can have mixing in regions that aren't convective, maybe due to mixing processes like waves breaking in the atmosphere. You have to have a huge opacity database for all the atoms and molecules you're going to have in your atmosphere. That needs to be pressure dependent, temperature dependent, wavelength dependent. And also you have to figure out what the opacities for your cloud particles are and how that changes with cloud particle size. So all these things are really going into any atmosphere model to some degree when you generate a model pressure temperature profile and a model spectrum. And so just like we have to make all these choices, we have to build up our different flavors of cakes based on different amounts of these different ingredients. I do have a couple more slides later on that do talk about desserts. So this is sort of not the last time you'll see this. OK, there's the next one. These are Skittles. OK, so in terms of atmospheres, there's lots of different varieties, right? So we've got the rainbow of fruit flavors. So I'll come back to this slide a few more times. The simplest, in terms of, these are all, most of the examples I'll be giving today are about giant planets, but towards the end we'll talk about looking towards the future a bit. So we have equilibrium chemistry, cloud-free. That's sort of the classic thing people were often doing in the 90s, and people still calculate those models today as sort of a basis of comparison. You also can have equilibrium chemistry with clouds, non-equilibrium chemistry, cloud-free. If you're not familiar with non-equilibrium chemistry, I'll be talking about that quite a bit over the next 5 or 6 slides. Non-equilibrium chemistry with clouds and maybe partly cloudy. These are the sorts of levels of atmosphere models you'll often see in the literature. So when I'm talking about atmosphere models today, I'm mostly going to be talking about what people call grid models or self-consistent radiative convective equilibrium models. Towards the end, I'll talk a little bit more about retrieval models and how these two things are related to each other. But grid models are sort of in some ways similar to stellar atmosphere models, where you might do a grid over effective temperature, log G, composition. These sorts of models are important in that you're putting in all the physics and chemistry you think you know. And so comparing the observations to the models that you have tell you if you're using all the correct physics and chemistry or if there's still room for improvement. So although in my talk today I'll be talking a lot about some of the things I'm involved in this Sonora collaboration with Caroline Morley, Mark Marley, Natasha Batalha in our groups, I'll also be talking about other folks' work as well. So in these grid models, you can generate a host of pressure temperature profiles. These are models over at a certain log G over different temperatures. This is comparing Phillips 2020 to Ames Kahn from, I think, 20 years previous. And you can see updates in things like chemistry and opacities lead to updates in pressure temperature profiles. Upper left here, Morley et al., 2024. These are cloudy equilibrium chemistry, models changing at different effective temperatures over a 16-year time difference for different effective temperatures, leading to differences in spectra. On the bottom left, this is Brianna Lacey's work, working with Adam Burrows, looking at very cold giant planets. I think it's 450, 350, 250. I know a lot of the discussion on Monday was very cold giant planets with JWST. And from these grid models, you get pressure temperature profiles, spectra, and you can do spectra over a very wide range of wavelength space. So I want to, instead of just sort of going through a laundry list of models, which I'll come back to, I wanted to talk a little bit about a particular science topic where I think we've made a lot of progress over the past 5 years or so, and that's thinking about non-equilibrium chemistry. And I'll be talking about some cloud-free models people have compared to observations. So this is a plot I'm going to spend a fair amount of time with. I think some folks are very familiar with non-equilibrium chemistry, but I think some folks are not, so I wanted just to sort of cover what this means in an atmosphere. So this is a plot that Didier Simon created quite a long time ago. I was a grad student at the time. I don't think I even knew Didier at the time. So I want you to imagine you're deep in an atmosphere and then coming up towards the visible atmosphere. So this is log of the temperature in the atmosphere. So this is down deeper where it's hotter. This is upper in the atmosphere where it's colder. So imagine we're moving along a pressure-temperature profile from hot to cool. You can think about the abundance of these molecules. This is the abundance mixing ratio of CO, methane, and water vapor. These are related to each other by this chemical reaction here. And when you're cooler, you tend to favor this side of the reaction. When you're hotter, you tend to favor this side of the reaction. And so we're going to imagine moving along. And there's two sorts of time scales we can imagine in this atmosphere. One is the mixing time scale, and one is the chemical conversion time scale. That chemical conversion time scale is really to move from the right to the left as you get cooler in the atmosphere. The deeper part of the atmosphere is convective. The upper part of the atmosphere is radiative. So let's look at the mixing time here. This is time scale here is log of the time in years. So deep in the atmosphere, where it's convective, you have a short mixing time. Convection's fast. Higher up in the atmosphere, where it's radiative, we still think that there's mixing to some degree, but at least in this model, it's many orders of magnitude more sluggish. We can also compare that chemical conversion timescale. Chemistry is a very strong function of temperature. So down deep in the atmosphere, where it's warm, this chemical conversion time is 10 to the minus 10 years, a really short amount of time. As we move up to where it's cooler and cooler and cooler, you can see the chemical timescale changes to many, many Hubble times, 25 orders of magnitude difference in timescale over a pretty narrow range in temperature. So down deep in the atmosphere, where the chemistry time is much faster than the mixing time, mixing doesn't matter. That's the region of equilibrium chemistry. Timescales don't matter. As we cross this cross here, that's called the quench pressure or the quench level. That's where mixing starts to be faster than chemical conversion. And so what happens there is that these chemical equilibrium abundances start to deviate. So in equilibrium, as you get cooler and cooler up in the atmosphere, the CO abundance should fall off by many orders of magnitude. But if you imagine this parcel of gas passing through that quench level, what happens is that you freeze in the abundances at the quench level. So the CO abundance is high. Correspondingly, the methane abundance has to be a little lower, and the water abundance is also a little bit lower. And so this has been known for a very long time. This has been known in Jupiter since the 1970s. Jupiter has CO-rich gas that's wafted up into the atmosphere from down deeper in the atmosphere. And we've seen this in brown dwarfs for decades as well. One of the big uncertainties, though, is how fast mixing actually is. This is really an important physical process. How fast is mixing? Deeper in the atmosphere where it's convective, you might be able to use mixing length theory, which is a one-dimensional model of convection. We don't know that that's really right, but it's a model you can use. In radiative parts of the atmosphere, we really don't have any sort of first principles model of how fast mixing is, so we'd like to be able to understand that from looking at real objects. This is typically modeled as a diffusion process. So this is a diffusion coefficient, KZZ. Higher KZZ is faster mixing. So this mixing time here is often some length scale, the pressure scale height squared divided by KZZ. So faster, higher KZZ, shorter mixing time scale, faster mixing. And so in these atmospheres, typically this chemical mixing time is unknown by a factor of 1,000 or more. But one of the great things about the era now is we have amazing spectra for a wide range of objects, and we can use that to measure atmospheric abundances pretty precisely and learn something about this mixing timescale in the atmosphere. And so we can do this today because we understand chemistry so much better. A wide range of lab work has allowed us to measure this chemical time scale as a function of pressure, metallicity, temperature. This is fitting a bunch of different models from a Zonley and Marley paper. The mixing time is really the thing we're really the most uncertain about. Mixing length theory, which I'm not going to go into in any detail, but it allows us to relate this convective flux coming up from the interior in terms of some KZZ that we'd like to know what that is. And then in radiative zones, which can be important in a wide range of atmospheres, we really don't know what it is. And this is important not just because of chemistry, which might seem a little esoteric, but mixing processes have a huge, huge impact on clouds. If you have strong mixing, strong updrafts, you can keep large particles aloft in the atmosphere. If you have very weak mixing, those updrafts aren't there and particles can sink down, and you can have just maybe very tiny particles in the atmosphere. There's a wide range of image planets and brown dwarfs where clouds are the dominant atmospheric opacity source. So it's not just about equilibrium chemistry, it's really about thinking about how mixing processes affect a wide range of physics, including clouds. So if we could understand these mixing processes better, that's going to unlock a lot of opportunity to thinking about the dominant physical and chemical processes. This is an example from Kazumasa Ono and a model he calculated of a particular salt cloud that might be found in T-dwarfs, just showing as you change the mixing coefficient by several orders of magnitude, it can change the mass of this cloud also by several orders of magnitude. So this really could be an important effect. So our first view into thinking about how mixing works in some of these atmospheres came from a really nice paper by Brittany Miles that I was lucky to be a part of. Using ground-based spectra in the mid-infrared, she was able to see CO at 4.5 microns being dredged up in very, very cold brown dwarfs. And one of the things she was able to do was sort of assess this KZZ, this diffusion coefficient, as a function of effective temperature for really cold brown dwarfs. Jupiter's over here, pretty vigorous mixing, 10 to the 8. Y's 0855, cold brown dwarf over here. And then for some other objects at the Y to T transition, she found that that mixing fell off by around a factor of 100. These warmer objects that have much more vigorous convection, a higher convective flux, seem to be mixing much more sluggishly. And one of the things we talked about in the paper is what might cause that, is there was a prediction going back to the 90s by Adam Burrows and collaborators, including Mark Marley, that some of these atmospheres, as you go to warmer temperatures, should actually have a radiative zone that we can't see, a detached radiative zone down below the visible atmosphere. In this diagram, this is temperature versus pressure. In black are radiative zones. So in the upper atmosphere, we're radiative. We transition to a convection zone. In some really cold objects, the convection zone goes all the way down, down, down. But at intermediate temperatures, where the opacity can actually be low, then you might have a detached radiative zone where mixing might actually be sluggish. We can't see this, but this might be evidence for that because it's below the visible atmosphere, but it affects mixing. And so Shagnik Mukherjee, who got his PhD in Santa Cruz, he's now a 51 Peg B fellow at Arizona State. We looked at this idea with new tools with the Picasso atmosphere modeling suite, thinking about how if we had a deep radiative zone, how that would affect atmospheric abundances. So here's a pressure temperature profile where it's radiative above, convective down below. We found for a wide range of models it's radiative, then convective, then this detached or sandwiched radiative zone, and then convective down below. You can calculate this chemical mixing time and then the chemical conversion time for a bunch of different molecules, CO, ammonia, CO2, HCN. You can look at where they cross, that same sort of quench level. For different reactions, you'll have different quench levels. And if the mixing gets very sluggish, this is this jog to very sluggish mixing by orders of magnitude, you cross at a different location, and it dramatically affects the atmospheric abundances you see here compared to here. So the chemistry timescales we can get from lab work. The mixing time, the idea was let's try to do this empirically. Let's look at real objects and have them tell us how fast their mixing is. This is just another slide for a given object, 700 Kelvin log G of 5. As you change this diffusion coefficient from very slow mixing to very fast mixing, you can see it has a dramatic effect on the abundances of things like methane, CO, water vapor, CO2, and ammonia. So by looking at spectra, if we can determine abundances pretty reliably, we really can have a window of how fast vertical mixing is. And this is borne out really well. This is a paper by Brianna Lacey, who's a postdoc at NASA Ames Research Center now. And she's looked at a wide variety of about 20 objects that all have really high quality JWST spectra from two big programs led by Jackie Faraday and Mike Cushing, trying to determine these mixing and atmospheric abundances as a function of temperature. And so what you can see is this mixing coefficient, KZZ, is a function of effective temperature. And indeed, what you see is this sort of interesting trend that the coldest objects, which have really the weakest convective flux, have the most vigorous mixing. As you get warmer and warmer and warmer, you actually get weaker and weaker and weaker mixing, suggesting, at least to me and to Brianna, the leader of this work, that we really are seeing this deep radiative zone deep in the atmosphere. The convection, the chemical conversion, the quench level is happening down in this radiative region. And so we're seeing very little mixing up into the atmosphere across a pretty wide range of these sort of Y and T dwarf objects. So to me, this is really exciting in that over the past 5 years, we've gone from an initial observation from the ground to using JWST and a new generation of models trying to fit these observations. I should mention that this is not just, she's done a wide variety of her own models, but she's also using ELF OWL and ATMO 2020++ models, and this sort of trend is robust no matter which particular models you're choosing. I think that's a really important point. So we really are making progress on this particular question as we move along in the field. And to me, I think that's really great to see. I want to, since we're of course want to be talking about planets, I want to mention that this idea of this deep detached radiative zone seems, at least within models, to have a very strong function of surface gravity. Generally, directly imaged planets are going to have lower surface gravity than field brown dwarfs. So this is a plot of log of the surface gravity versus effective temperature. These are different choices for how to treat mixing. This uses mixing length theory. This uses a tenth of mixing length theory. We also, of course, don't really know how great that is. Field dwarfs are going to tend to have higher surface gravity. Planets are going to tend to have lower surface gravity. The hashed region is within the framework of the models where we think we're quenching in this detached radiative zone, and the CO abundance should be low. That's the blue color, CO poor, whereas red is CO rich. And so we actually think that there should be a very strong function of gravity that affects the mixing processes in the atmosphere. So within this prediction, as we get to these lower surface gravity objects, we actually think the mixing should actually be more vigorous, and we really should see a meaningful difference between the planets and the brown dwarfs. This is something I hope we can see as time goes on. We go back to the Skittles. So I want to talk a little bit now about where some of the models that I'm involved with fit in, and then also models that I'm not involved with, how they also fit in terms of what's the state of the art, what used to be the state of the art, and where things are going. So this is a very nice poster that Caroline Morley made for the Exoclimbs that people got a lot of attention. It was, well, God, there's so many models now, like, help me figure out what to use. And so she loaned this to me, and we're going to zoom in on this just towards the bottom here. So within the framework of our collaboration involving myself, Caroline, Mark Marley, Natasha Batalha, and our groups, I know you had a talk from James Mang on Monday talking about some of these models. We have Bobcat, that was the first set, that's equilibrium chemistry, cloud-free. I'll talk about this in more detail, not just this slide. ELF OWL, non-equilibrium chemistry, cloud-free. Diamondback, equilibrium chemistry, cloudy. Flame Skimmer, in progress, non-equilibrium chemistry, cloud-free, colder and lower gravity. And then Gila Monster, very cool animal. I only ever saw one in the 5 years I was in Tucson. Non-equilibrium chemistry, cloudy, and I think we'll do some partly cloudy models as well. So I want to talk about why these are useful and then how we might compare them to other sets of models. Okay, so this is my last candy reference, Mounds, Almond Joy. Sometimes you feel like a nut, sometimes you don't. There's different parts of the models you might want to include or you might not want to. So equilibrium chemistry, cloud-free. In terms of what's going on today, that's Sonora Bobcat, Atmo 2020, CEQ, the Beck's models from Linder et al. For very cold objects that folks are using for cold JWST spectra. You know, they're really important as a baseline. We should never really expect equilibrium chemistry cloud-free to be that close to reality. If you're warm enough that equilibrium chemistry might be okay, you're typically also going to have silicate clouds. If you're cold enough that maybe those clouds are gone, you're probably going to be in a regime where you need to have non-equilibrium chemistry. So it's going to often be the case that these models maybe aren't going to fit reality, but they're really an important starting point. They're also the easiest ones to calculate, but it's a good starting point to think about deviations from that, with the thought that pretty much everything is always going to deviate from these models. Some older models within this framework that I'll talk about a little bit later on are things like Burroughs et al. 1997, some of the Baroff et al. Allard models from previous decades too. Thinking about equilibrium chemistry with clouds, and by most of the clouds we're talking about silicon and iron clouds, of course there's other sorts of clouds. Sonora Diamondback, that's a paper that Caroline led 2 years ago now. Another variant is ExoRem, led by Benjamin Charnay and his collaborators. So they have, of course, a different framework. They have a different cloud model, and they have different ways of treating chemistry. So they have a paper, and I looked online, and they have another paper, I believe maybe led by a student that's supposed to be coming out this year as well. There's the famous Marx atmosphere modelers who've done a lot of work in stellar atmospheres. They have a paper from 2014. That's MSG. That's a collaboration between the Marx atmosphere modeling and Christian Helling's cloud model that you might be familiar with. So they have a paper in 2024 that's sort of a proof of concept. They haven't yet, I looked, sort of released big grids of models, but they're doing cloudy sort of L-dwarf models as well. And then the Beck's models from Linder et al. Are also cloudy, but again, relatively cold objects. And so these models are, to various degrees, sort of state-of-the-art, and it's good to compare across models because people are making different choices about how to treat chemistry, how to treat clouds. Cloud models are always evolving. As we look towards the more distant past, there's BT Settle models. Of course, Franz Allard sadly passed away. And so these models have a whole different treatment of clouds, but of course they're not being updated. And as time goes on, everyone tries to, of course, update as new opacities come out, new line lists, new treatment of chemistry. There's also Drift Phoenix, which is a collaboration, again, between some of the Helling and Wittke models and also the Phoenix collaboration. And sort of down on the right here, there's a figure that James Mang was prepping in terms of thinking about just sort of the phase space of a variety of these models and where they are. Wanted to jump to some more kinds of models. We have non-equilibrium chemistry, cloud-free, which might be appropriate for sort of a wide range of T and Y dwarf and those sorts of objects. Sonora Elf-Owl, Atmo 2020, NEQ, that's the non-equilibrium chemistry version. Sonora Flame Skimmer, that's in progress. And then Atmo 2020 by Tremblin collaborators. That's the same code, as you might expect from Atmo 2020, but one of the things they've been looking at are changes to the deep atmosphere. If you get away from this idea of having to have adiabatic convection as a free parameter, you might be able to fit spectra better. And so again, all of these papers are looking at similar sorts of objects. As we go to non-equilibrium chemistry with clouds, to me that's sort of the hardest thing to try to pull off, because your cloud model might need some sort of assumption for how vertical mixing is operating. And your chemistry needs some sort of assessment for how vertical mixing is operating. And you might have sort of picked those to sort of fit spectra the best, but you need to sort of marry those two into the same model. Ideally, you want to have one kind of vertical mixing that both affects the cloud and the chemistry. And so that's still something people are working on. So Lacey and Burroughs have done that for, again, cold objects, both their paper that's published and that paper in prep I mentioned about 10 minutes ago. They've also done cloud-free models as well with water clouds. The Sonora Gila monster models are going to look over a fairly similar phase space as well. And although the big grid of models, to my knowledge, isn't published, within the Marx model, they've been looking at non-equilibrium chemistry and silicon and iron together. And so I apologize if I missed anything. I really did try to delve in over the past week and looked at everyone's papers and websites, and I think this is reasonably close to comprehensive what people are trying to do. And I think it's really important to use a variety of models because people make different choices, and we're all trying to drive towards a better understanding of atmospheres. How to help? So, of course, atmospheric retrievals are really important these days. Retrieval is, of course, a methodology where you take the spectrum that you see, and you might run thousands or tens of thousands of models to find the best fit pressure temperature profile that yields the best fits. Those are, in some degree, physics and chemistry agnostic. The idea is to sort of let the spectrum tell you what's actually happening. And those models can be quite powerful. But I think it's really important to remember we're trying to figure out the physics and chemistry. It's really important to compare a retrieval model to a grid model to sort of think about why the grid model is failing. Because the grid model has all the physics and chemistry that we know. If there's a failure to fit, that is an opportunity to learn something. So here's a particular retrieval from a T-dwarf led by Callie Hood. The closest fit elf owl grid model is reasonably close to reality, but you can see down below the best fit in orange involves web data, specs, and Spitzer, and you can see there's a deviation where the retrieval finds a cooler, deep atmosphere. This is just one particular object, but if we, as a community, try to do comparisons like this anytime we have a spectrum and do a retrieval, we can then start to build up trends about things like, is your upper atmosphere always a little bit too cold, which I think is a trend we're starting to see? Is the deep atmosphere always a little bit too hot? Some objects show this really dramatically, some not so much. If we can understand that as a function of effective temperature or surface gravity, that is input to thinking about what the models are missing in terms of their physics and chemistry. Wanted to change gears and do a couple slides on thermal evolution models. Of course, for direct imaging, these models tend to be critically important because we often don't know the masses of the objects. Of course, that's radically changing now with dynamical information, which is really helpful to test these sorts of models. If we have an age, a luminosity, and a mass, we can test these models in a way that we've never been able to for a long time. And these thermal evolution models are important because they're another test of the atmosphere. These grids of model atmospheres serve as the upper boundary condition for the thermal evolution of these objects. They're intimately tied together. So if the evolution models are not accurate, they could point to deficiencies in the atmosphere. And so I just grabbed a few different slides. On the lower left, this is Phillips et al. Working in collaboration with Chabrier and Baroff, looking at how the cooling of objects from sort of planetary masses to brown dwarf masses, you can see some deuterium burning over here, to stellar masses, how that changes with the equation of state of hydrogen. This has been something that has changed recently for many years, or decades. People use the Simon-Chabrier equation of state. There's been an update by Gilles Chabrier to two new equations of state. And this has, I think the biggest effect actually is in terms of sort of what is the mass of the hydrogen burning limit. You can see for some of these cool objects, it's not a huge difference, but it does really make a meaningful difference to some particular quantities. On the upper left, this is a plot of thermal evolution models where we were worried about what is the initial condition, hot start versus cold start. This was a classic sort of older paper now, where the initial conditions for how hot you would start out initially could have a big impact on your evolution at sort of younger ages, not so much as older ages. On the far right is a new paper from part of the Diamondback series. So red Diamondback are evolution models and spectra that attach to Diamondback, going to even hotter temperatures to very young brown dwarfs will be M-type objects. So this is a plot of radius versus mass at 1 million years, 10 million years, 100 million years, and gigayears. And of course, objects are quite young and fluffy and warm when they're first formed, and they contract over time. I like this plot because it has a lot of little interesting tidbits here. A lot of these weird bumps and weird bumps here are due to deuterium burning. It's sort of interesting that for these really cold objects right around 13 Jupiter masses, even after 1 billion years, you can still see a little bit of interesting physics due to deuterium burning. You can also see when things transition from being brown dwarfs to real stars over here. So I thought this plot was pretty interesting. It also shows the effect of atmospheric metallicity as well. So these sorts of thermal evolution models can be tested now in a very meaningful way because we're often getting dynamical masses at the same time as we're getting luminosities with age estimates. Again, for thermal evolution models, as I mentioned, the atmospheric boundary makes a difference. So I would say the state of the art for going from warm to cool is to do cloudy to cloud-free atmospheres. We know warm objects have these thick silicon and iron clouds. Cooler objects do not seem to have them. So this is what we've been doing in Sonora Diamondback and the Sonora Red Diamondback, which goes up to warmer temperatures. This is a plot of effective temperature versus age. The warm young brown dwarfs are on their little Hayashi tracks where they have relatively constant effective temperatures before they start to cool off. Here's an implementation of the L to T transition where you go from cloudy to cloud-free. You get these jumps in the evolution because you have a lot of stored thermal energy that can't get out because of the high cloud opacity. When you take that cloud opacity away, that residual flux is able to finally break its way through, and it has a real quantitative difference on the thermal evolution tracks. Cloudy atmospheres, again, the Linder et al. Models looked at salt and sulfide clouds just for very cold objects. There are cloud-free evolution tracks, Sonora Bobcats, Atmo 2020, Phillips 2020, and then very recently a Chabrier 2023 paper that uses the same Phillips atmosphere, but an even newer update to the equation of state. So things really are changing as time goes on. Looking back a little bit towards the past, there's, of course, models that look at this hot start and cold start from, gosh, 15-ish years ago. Folks haven't really come back to this in a ton of detail since then, just because there hasn't been a huge amount of change in this uncertainty in our initial conditions. But as formation models get better and better, this is really something that I think people will come back to, thinking about how formation affects the early evolution. And then, in my opinion, sort of, I think just too old to keep using are some models that really use older physics in terms of atmospheres. So Burroughs 97, Kahn, Dusty. So these use atmospheric boundary conditions that just we know are out of date. And these really do not use the updated physics and chemistry that we know can fit the spectra. And so in a lot of cases, these can have relatively modest impacts on evolution. But as folks are generating newer up-to-date models, these will really give you our best test of the physics and chemistry that we're trying to get. And this really can have a meaningful impact. This is one of my favorite figures over the past sort of 5 years in brown dwarfs. This is Kirkpatrick 2024, the 20 parsec sample. This is sort of number of objects versus effective temperature. And these are models, so the data is in black and models are in red. This is sort of a population synthesis of star and brown dwarf formation over time in the galaxy. And so it turns out that in the solar neighborhood, there's this weird overabundance of 1,300 Kelvin objects. It's a real thing. And it turns out, we think, that it's due to this effect right here, where you're sort of letting the valve off. You stall the evolution of a wide range of objects, and if you stall them at 1,300 degrees, you have an overabundance of things at 1,300 degrees. And if you have evolution models, like these older Barath models that don't have clouds, you don't have this stalling effect, you don't reproduce this effect here. So these models were from the older generation of Saman and Marley, but the same effect was included, that you have this sort of release valve on atmosphere. So there are real, meaningful evolutionary effects where the models that you choose have a big impact. And so I think it's a really fun thing that in our solar neighborhood, there's this overabundance that seems to be due to the L to T transition. All right, I just have about 30 seconds left and just a couple more slides. Where are we going? Great question. So there's all sorts of cool stuff happening, as we all know, right? So one of the things that I think is really amazing is on the extremely low metallicity side. Is this relevant to planets? I don't know, maybe. But there's really low metallicity brown dwarfs, maybe like 100th solar metallicity being found. And they have crazy things in their atmosphere, like silane, which sounds like an alien sort of race of people or something, and phosphine. This is a paper led by Jackie Faraday, and you can see at around 4.5 microns, there's this really strong absorption feature there that is due to SiH4, this sort of equivalent of methane, but with silicon. Some isolated brown dwarfs are showing temperature inversions. They don't have energy from their star pumping energy into the upper atmosphere, but they have inversions anyway, or they have upper atmospheres that are too warm. That indicates we need additional ingredients in our cake recipe, additional heating in the upper atmosphere. People are developing new and different one-dimensional cloud models. This really needs to keep happening. We need new ways of thinking about how clouds are affecting atmospheres. This can be coupled to one-dimensional atmosphere models. We can also think about maybe multi-column one-dimensional models where you can call the radiative transfer on thick and thin clouds at the same time. People are working at higher metallicities for cold Neptunes. As we try to get ever smaller and colder planets, they might well have more metal-rich atmospheres. And there's a demand, I think there's going to be a demand for one-dimensional models for a long time. We can explore a really wide range of phase space in one dimensions. But these models can be informed by what people are doing in 3 dimensions, and they can be informed by one-dimensional retrievals, and that really needs to keep happening. Lastly, we can also be informed by the solar system. There's been a suggestion that Jupiter and Saturn have diffuse and fuzzy cores. And there's people working in Adam Burrows' group who have developed this Apple code to look at how fuzzy cores might affect the early evolution of giant planets as well. It's another topic people are working on. Second to lastly, we're trying to be receptive to new observational capabilities. I know there was a lot of talk about Roman CGI yesterday. Zara Brown, who's a postdoc at University of Arizona, is working on models customized to thinking about what we can do within the Roman bandpass. So my takeaway messages, I'll briefly mention them. We can use chemistry to learn about the physics and chemistry of atmospheres, to learn about mixing processes that are important with clouds and chemistry. If you're doing retrievals, think about comparing to grid models too, because that's where this learning is happening. We can see the model's deficiencies. And folks are always putting efforts into new models. Please use them if you can. If you're having trouble using them, talk to us about how to make them easier to use. Thanks. Happy to take questions.
Well, that was a really informative talk. I'm sure we could spend all morning learning about the ins and outs of modeling, but we have time for a couple questions. Sure, go ahead.
Hi, thanks for the great talk. Aniket Sanghi from Caltech. So I was curious about KZZ in the radiative zone you highlighted, our lack of knowledge in that area. I saw in the plots that the mixing timescale is changing in the radiative zone, so I was curious, are you parameterizing as a function of temperature, or how are you treating it in the current models?
Yeah, that's a great question. So in some models, we've just freely parameterized it. Let's make a grid of models that go from really low KZZ to high. We can just have those, and we can then compare them to spectra. In other modeling frameworks, we've really tried to be high precision, where we use mixing length theory or some version of that in the convective zone. And then in the radiative zone, people have made suggestions for what that is, and then we can use that and then go back to mixing length theory and then go back to the radiative zone. In that, I think that's the ideal, because the quench levels can be different for the different chemical species. So some could actually quench, like CO2, let's say, could quench in the convective zone, whereas another molecule might quench in the radiative zone. And so in that way, you might be able to crudely determine mixing as a function of height. So in that sense, a more sophisticated model that really aims to look at the atmosphere zones would actually be a little bit better, but people have done both.
Hi, great talk. This is Eleonora Alei, NASA Goddard. I approached this from a slightly different perspective. I do retrievals,
Yeah.
but for next generation missions. And
Yeah.
we do use sometimes grid retrievals. So we
Yeah.
leverage grid models for our retrievals. I was wondering if this is something that could be done for your case as well. So, because it seems like your grid models are definitely higher fidelities than what we use. But you're also
Yeah.
not stuck necessarily to using live retrievals,
Yeah,
if you will.
yeah. I had a slide on that, and I took it out last night. So yeah, you can do retrievals with grid models, especially today, since people are computing not just grids of 100 models, but grids of like 10,000 or tens of thousands of models. So I think that's a really nice complement, because the grid models, of course, already run. So you can of course get some interesting answers much faster. So I totally think that's a great idea.
Yeah, thank you. Yep.
Maybe take one more question, and then while we switch over to speakers.
Kim Ward-Duong, Smith College. Thank you for the wonderful review. I was curious a little bit about the properties of the detached radiative zone and how that might relate to the amplitude of variability that we see around the LT transition.
Yeah. You could totally imagine that as the object rotates, and people have, like L.C. Lee has shown something like this in 3 dimensions. You could imagine that some parts could be updrafts, some parts could be downdrafts, and that the width of that radiative zone could actually change with sort of latitude. And so that could lead to chemical abundances changing with latitude, and that could be part of variability in chemical abundances. But that also could lead to, probably even more dramatically, changes to the cloud structure because of those updrafts and downdrafts and the changing sort of the thickness of that zone. So I definitely think there could be, that could be an important part of variability.
Thank you.
Yeah, especially since variability is highest at the L to T transition, it seems like. So yeah.
Excellent. Well, thank you again.